time schedule here. Can everybody hear me okay? Yeah. I would start with the most simple CT reconstruction called filtered back projection. This type of reconstruction has many limitations. For instance, in filtered back projections, we assume that the focus spot size is infinitely small, like a dot. And the most famous focus spot size in the world or in the universe is perhaps the sun. And if you hold out your hand and you look at your hand on the floor, you can see that it's very blurry. So a need to simulate a proper focus spot size is obvious, of course. Filtered back projection also assumes that the radiation beam is like a pencil beam without a polychromatic spectrum, so very thin beam and no polychromatic X-ray spectrum. And also each voxel inside the patient is considered infinitely small, so we don't have a size and shape on the voxels in the patient, they are just small dots. And the same thing goes for the detector elements, they are also considered infinitely small. So everything is basically dots and pencil beams in filtered back projection. And in filtered back projection, you will also have a trade-off between spatial resolution and noise, which is linear. So if you increase your noise, you will also decrease your spatial resolution. This gave a need for iterative reconstruction, and the most modern iterative reconstruction from all vendors are called hybrid iterative reconstructions. And in hybrid iterative reconstructions, you can model noise more properly than you can in filtered back projection, which means that you can reduce some of the limitations between trade-off between spatial resolution and noise. But these reconstruction algorithms mainly performs in the image data domain. So you have your raw data, you use a reconstruction kernel, you do your iteration loops in the image data domain, and here you can reduce noise quite a lot. But you cannot improve spatial resolution. You will have a decrease in spatial resolution because you can only model the noise with these kind of algorithms. You cannot model the optics of the system. You cannot model the voxels in the patient. You cannot model the size of the detector elements. So you will have a very effective noise reduction, but you will decrease image quality. So this calls for a need for true modeling in iterative reconstruction. You need true modeling of the system and the patient. To take the next step in image quality reconstruction in CT, you need true modeling of the focus spot size. You need to model the detector elements, also the patient, and the entire system geometry. The beam energies have to be modeled, because when the X-ray beam travels through the patient, you will also have beam hardening, which will affect image quality. You must also model the cone angle, the shape of the beam, and also the electronic noise from the system, which becomes even more important now when we do low-dose scanning. And the goal of all this modeling is, of course, to improve noise or decrease noise, and at the same time have no decrease in resolution. So you want to maintain your spatial resolution, at the same time decrease noise. And to do that, you need to apply all these models. And this is why Toshiba released the reconstruction algorithm called FIRST during RSNA 2015. And the name is Forward Projected Model-Based Iterative Reconstruction Solution. And the key word here is forward projected. To apply all these models, you need forward projections. And I understand this is a very difficult image to grasp for 5 minutes, but I have to show you anyway. The idea of a forward-projected iterative reconstruction, which mainly takes place in the raw data, is that if you look at the top of the image, you do your normal reconstruction, and after you do your normal reconstruction, you apply a forward projection. And when you apply a forward projection, you're basically generating new raw data. And at the same time, when you apply all these models I explained in the previous slide, then you can compare your reconstructed data with your measured data. So you can validate your reconstructed data by the help of the models. If you do this in the image data domain, you can never validate your reconstructed data. You have to go back to the measured data and compare the differences. And if they are small or good enough, then you have a good image. If they are not good enough, then you have to apply a new raw data loop. So this is the only way you can validate your results, so your reconstructed images. And also to apply, for instance, the optics model, to model the shape and size of the focus spot, you need a full raw data iteration loop. It's impossible to model the optics in the image data. To model the cone beam, you also need a full raw data iteration loop. It's impossible to do that in the image data. And to model the statistical models, you also need to do that inside the raw data, because you want to perform low-dose scanning, you have low energy data in the detector, and you need to do regularization in the raw data domain. So the message is you need this. Okay, what can we expect from FIRST? The purpose of FIRST, here is a comparison between filtered back projection, and you can see for high dose levels that we have low noise levels with filtered back projection. But the purpose of FIRST is that you can reduce your dose dramatically and maintain the same noise value. So by applying all these models and regularization in the raw data domain, that you can reduce noise and perform low-dose scanning without decreasing image quality. I would do this slide quite fast. The problem with iterative reconstruction is that you don't remove all kind of noise at the same time. You mainly remove the high-frequency noise, and you have a noise power spectrum, which shows the shape of the noise, basically, and this will impact your image quality. So if you look at it in the down left corner, you can see the top right square, you can see kind of plastic-looking images. This is the effect you have when you reduce noise and remove the high-frequency noise. And FIRST has a model incorporated that means that you will, for the same regularization strength of FIRST, you will have the same peak frequency regardless of dose level. So the goal is to have the same image appearance regarding dose level. And this is also measured spatial resolution with FIRST and compared to filtered back projection, who is really the golden standard for spatial resolution. And you can see that with FIRST, we can even increase spatial resolution compared to filtered back projection, which is not the case, of course, with hybrid technologies. So in summary, FIRST is the fully statistic reconstruction algorithm, model-based. We do advanced modeling of both the scanner and the patient. We reduce those with preserved image quality, which has not been able to do in the past. We have better contrast and detail resolution compared to filtered back projection and hybrid IR solutions. And it's also integrated in the protocol for using optimal scan parameters to benefit the reconstruction. Thank you. That was a little bit more than 6 minutes. I'm sorry. Yeah.